Like honestly, I
Okay, shall we? Yeah.
I have been tempted to even.
Oh, the register.
Well, merci beaucoup.
You are so wow.
As they say in my home one. Beaucoup.
Okay, so a group acts on something, okay? Does that mean that a group acts on something? You've got your group elements are some kind of operations that are doing something to a set, which we usually call X in this book. And all these operations you can compose, so you do one after the other, which corresponds to the group multiplication thing. And all the operations you can reverse, which corresponds to the inverse in the group thing. That's an action. Now, one thing we did with actions was orbits. Yeah, does everybody know Conrad?
Oh, what's not?
So when you've got your set X that's been acted upon by the group G, what? So every element can be moved to some other elements, maybe only to itself, by all the group elements. And so all these elements of X that can be moved one to another by a group element form an orbit. Okay? And so the set X orbits are what's it called? Classes of an equivalence relation. Okay? So it's a partition of the set into orbits. And what did we do? We looked at a simple thing which says that the size of the set X is equal to the sum of all the sizes of all the orbits, because it's a partition. And now in a special action, which is by conjugation, where these bits that can only move onto themselves, they form what's called the center of the group. Z for Zentrum, it's a German word. So that's all of them, and then you add the sizes of all the remaining orbits, and each of them has size that we proved is equal to the index of a certain subgroup, which is called the centralizer. Oh, that is. Where are the definitions? Somewhere here there are the definitions. Oh yeah, the definitions. So the center is, so the action is, what an element of the group does to an element of X is it sends it to GXG inverse, because this set X happens to be the group itself. There's this one specific action that we're talking about, and the center is all the ones that stay put, no matter which element of the group you use, which is equivalent to commuting with every element of the group. That's called the center. And all the orbits are called conjugacy classes. And all right, and the stabilizer. So what's the stabilizer? That's all the elements of the group which, for a particular point in set X, don't move it anywhere. Well, that's all we were doing. And so then the equation that size of the set, which is now equal to the group, set is the same as group, is equal to the sum of all the sizes of the orbits. That's this. And that's all we ended. And then the book has examples. So, for example, it's S3. So what are the conjugacy classes? Okay, so what's the center? The center of S3, that's by definition all the elements of S3 that commute with everything else. What commutes with everything else? In S3. The identity always does. But nothing else. It's quite easy to check because you've got 1, 2. When you do 1, 2, 2, 3, it's not the same as if you do 2, 3, 1, 2. So no 2 cycle commutes with everything else because it doesn't matter that I took 1, 2. Could have taken any other one. And it's the same for the 3 cycles, of which there are only 2, 1, 2, 3, and 1, 3, 2. Are they the same? 1 goes to 2, goes to 1. Whereas here, 1 goes to 2, goes to 3, so they're not the same. So 1, 2, 3 doesn't commute with everything. So 1, 3, 2 also doesn't commute with everything. So that's the center. And then there are how does this work? It's a special case of example. There are 2 more. Yeah. Okay. Which you can either check directly because it's just not. Or you can look at example 1414. So this example is silly. Everybody can sleep. Okay, how does this work? Do you know what conjugacy classes are at all?
Yes.
Okay.
Conjugacy classes are non-trivial.
Yeah, or sometimes even the trivial. But then in this particular action, okay, so what I'm saying is if you take a 2 cycle, any 2 cycle, AB, and you take another permutation and put it like this, that this is going to be a 2 cycle again, CD. Okay? Basically, because that means that all the 2 cycles are in this conjugacy class. And so by acting on it in this specific action, so when I take, that's what I call a sigma, and that's my 2 cycle. What I'm getting is sigma 2 cycle, sigma inverse, and I'm claiming that this is an orbit, which means that I'm claiming that whatever I do, whichever sigma I take, from a 2 cycle, I always get a 2 cycle if I do sigma AB, sigma inverse. Okay, that's the, and also that I can get them all. But that's, so I think actually what you're getting is sigma of A, sigma of B as a two-cycle. That's not true.
Is sigma another element?
No, sigma is another permutation. Yes.
Yeah.
Another permutation in the group. Yes,
Yeah.
correct. Yes. So what I'm saying is, if I take any two cycle and any other, well, even the same element, I'm always going to get a two cycle again. For example, give me your favorite sigma. Well, it looks like I'm not listening, but I wrote sigma on this. So actually, your sigma is 132. But what you're doing, okay, so where does one go? Well, one goes to two, then something happens to it. Oh, this is not working. I'll put 1, 2 for this one. So 1 goes to 2, goes to 1, goes to 3. And 3 goes to 1, goes to 2, goes to 1. Okay, so they're actually really getting on. That's a cycle. And what is sigma of 1? 1 is A now. Okay. What is sigma of 1? It's 3. And what is sigma of 2? It's 1. Okay, so you're supposed to be getting 3, 1, 2 cycle, and you're actually getting 3, 1, 2 cycle. But that's not a proof. But at least it's not a counterexample. Okay, so the class equation, that's this one. There it is. The size of S3, the order of S3 is 6. The center, we said, is only one element. And there's this orbit that has 3 2 cycles, and then there's this orbit which has 2 3 cycles. That's what the book wants you to believe. I don't know. Doesn't make it any clearer to me. So I don't know. How about example 14? Thing is just the identity. Oh, it's theorem 6.16 apparently. Oh, that's Killian's theorem. Does that look familiar?
No.
I'm now brought on the page. Or not. Yeah.
I've also written on the page, but I'm a bit bothered.
Okay, so this theorem says that two cycles have the same length if and only if they're a conjugate of each other. Okay, so you know how this works. Now, if you have a permutation that, well, any permutation, you can write as the product of disjoint cycles. Right? Okay, so then what is sigma pi sigma inverse? Well, you can write it as sigma tau 1, sigma inverse, sigma tau 2, sigma inverse, so on. So sigma tau k, sigma inverse. And not. So these are going to be disjoint cycles again, of the same lengths as the ones before. So when you do a bit of argumentation about it, you get that two permutations are conjugate only if they have the same cycle structure. Which is the lengths of the disjoint cycles. Okay. So there's a length of tau 1, length of tau 2, and so on, up to the kth length. and then any conjugate permutation will have exactly the same lengths of cycles. For example, these are all the cycles of length 1. These are all the cycles of length 2. These are all the cycles of length 3. There's nothing else in S3. But S4, well, it has the center, which is all the cycles of, there's no length of length 1, something like that. And then the remaining conjugacy classes, you have all the 2 cycles. 3, 4. Then you have all the 3 cycles. And you have all the 2 plus 2s. What else is there? 4 cycles. So 3 cycles, that's like 3 plus 1, because there's the remaining element. This is like 2 plus 2, we already said that. This is like 4. This is like 2 plus 1 plus 1. And this is like 1 plus 1 plus 1. 1. Does that make any sense? How many of these? There's only 1. How many 2 cycles?
6.
4 choose 2. How many 3 cycles? Hard work. How many 3 cycles?
You say 8. No.
Yeah.
Is that right?
Yeah, why?
Because you'd have 3 more versions of those, but with different numbers. That doesn't make any sense.
Yeah.
It makes sense in my head.
That is. Yeah. So if it's a 3 cycle, one of the 4 elements is missing. And for the 3, there are 2 directions, remaining 3. So you've got 4 options for the missing element and 2 options for direction, which gives you 8. I guess that's what you said.
That is what I meant.
And
What I
then
said.
yes. Today I'm having
Sometimes-
trouble with distinguishing what people mean and what
Sometimes it's
people
not what
say.
you meant rather than what you said. And I'd like that reflected in
Yeah, same. Oh, God.
Another way is, say, like, the first thing, you've got 4 options, times 3 options for the next one, and 2 options for the last one, so that's 24. But then each of them you counted 3 times, depending on whether you're starting with the 1 or with the 2 or with the 3. So that's 24 divided by 3, that's 8 as well. Okay, how many 2 plus 2s? I think they're all there. How many 4 cycles?
Oh, No, no, I mean the rest of the.
Right.
6.
How'd you get that one?
I feel like there should be 24 and we've got 18 so far. Yeah, but is it? Because we don't even know if it's right. Never mind cheating.
I don't know. How'd you do that? Like you'd always start with 1, and then you have 3 different options, and then you have 2 different options. 6. So 24 is 1 plus 6 plus 8 plus 3 plus 6, maybe. It's amazing how you need 1.5 terms of group theory to be able to count by that. Apparently. Oh, now my notes are starting to be interesting. Example plus. I know you like it. Matrices. So there was this thing called similar matrices in linear algebra, as I'm sure you'll remember. Probably because Stephen have told you. So A and B are similar. If A is CB, C inverse for some other matrix, maybe the same. I don't know what it is like. If A and B are similar, it's kind of clear. But also the traces are the same. I don't know what a trace is. Good.
I don't see. You do something on the diagonal, don't you? What do you do?
Sum the diagonal.
Right. Do you just have the diagonal?
Yeah, it's a very simple thing.
Right, okay. I did know then.
Much easier to do than the determinant. I think they have the same eigenvalues. Is that right?
Not got a clue.
Yes.
Are you just yeah, right.
Are you googling the same eigenvalues? Could do. Confirm it. I haven't got any more today.
I don't even know what eigenvalues are because I do eigenvectors when you say eigenvalues. So it's not even.
Do you want to know?
No, I do know, yeah. It's just I did the wrong thing in the coursework and I lost 2 marks because I read eigenvalues and did eigenvectors.
I think if I did that when I was a student, they would just fail me. No regard to whatever else I knew. Okay. Maybe you should just not listen to me.
I did learn the method. I read it in the book. I just read the wrong word, didn't I? Yeah, sorry.
No. I'm trying to work on linear algebra because I'm too lazy to do group theory today. So.
Yeah, we haven't got an exam that we need to pass in this, not linear algebra.
Yeah.
Nothing wants it.
So what is a, like you have these things, they're called coordinates, right? So normally, but every A-level student knows that is that you take two vectors, the one that is a 0, 1, and this one that is a 1, 0, okay? And no matter where you go, like here, what is this? Like 5, 3, maybe. Or thereabouts.
Well, like 5, but you know, whatever.
No, but they're smaller here, so maybe it's 5, 8.
Definitely not.
In any case, this means that it's 5, 8, means that it will take 5 times the first vector, which is 1, 0, and you add 8 times 0, 1, right? And that's why 5, 8 are called the coordinates of this particular vector with respect to this basis. Okay, so you have a basis which is 0, 1 and 1, 0. I'll write it as a list. And then this is a basis. And then this vector u has coordinates 5, 8 with respect to b. Because it's 5 times the first thing, no. I wrote them wrong. It should have been 1, 0, 0, 1. Is it still making sense? Okay. But you can have a different basis. So how about if you had a basis which has like 1, 1. Minus 1, 1. So we have new basis which has, why am I doing this?
So I'll leave some interest down.
So now you have this matrix which is 1, 1 minus 1, 1. And that converts the coordinates. And C inverse converts them back. So what is C inverse? Well, it'll be some 1/2. Then there has to be a minus somewhere. So yeah. Yeah. Okay, that's the inverse. Because when you multiply them, you get the identity matrix. So now when you do C inverse times some coordinates like 5 and 8, okay? 5 and 8 were the coordinates. You get 13/2. And this was their coordinates. And this one is 8 minus 5 is 3/2. Okay, so U has coordinates these new ones, 13/2 and 3/2, with respect to the new basis. Because if you do 13/2 times this, and 3/2 times this, you get 13 minus 3 is 10, 10/2, that's 5. Oh yeah, that's what we wanted. And this one should be 16/2, okay, that's 8, that's what we wanted. Okay, so that's how it works. So this is what a matrix does with coordinates. Now, what does a matrix do normally with vectors is a linear transformation. We talked about this. So it moves vectors around so that straight lines stay straight lines. Now, if you have a matrix, and you know this is a linear transformation, okay? And this, sorry, not sure. And this works with the standard coordinates. But for some reason, all your vectors, you only know their coordinates with respect to this basis. So what does it do? Well, you want to convert the coordinates to the original ones, which you can do by... So if you want to know what this linear transformation does to it, so you convert the coordinates, and then you do the transformation, and then you convert them back to the weird ones. So if you times this by the new coordinates, like 13/2, 3/2, okay, C gives you 5/8 times this, then A does something to 5/8, and then the C inverse gives you the coordinates of that again. And this is a matrix similar to A. So somehow, it's like the gist of the example is that similar matrices represent the same linear transformations with different coordinate systems. With respect to different. End of example. The wrong chapter. That's boring. Do you have any questions?
I don't.
Anybody else? I'm starting to feel like that's enough for today. But we have exciting things to do tomorrow. Counting the number of ways to color an object.
Before the time.